I don't expect you to really think much about my video and writing and my oratory skills or all that, but I have something here that works that you don't find everywhere, and I'm able to explain it. If you can just get through some of my, you know, I don't know what to call it, but I'm not a good orator or an experienced teacher, but I know that what I'm talking about here works, and I'm putting it right before you to see. And this is good for people who are really well experienced with music but haven't really dabbled in the geometric and mathematical aspect of music theory. It's not that hard. It doesn't go much further than the kind of geometry that you do, you know, in a grade school level, and the mathematics doesn't go any further than arithmetic. You might have a complex array of arithmetic, but as far as calculations, no, you're not going to do anything more than arithmetics, and you're not going to add anything up more than 12. Even when you do a few pieces of division, you're not going to divide anything more than maybe 12 by 6, 12 by 2, divide 12 by 3, divide 12 by 4, maybe multiply 3 by 4, maybe multiply 4 by 3, and 2 by 6, and that's it. And then the arithmetic is going to be no more than adding and subtracting things that add up or to no more than 12. And it's because that's all we're dealing with here, 12. So you don't need long division skills and multiplications of you know, 4-place numbers and all of that, or decimals. Nothing. Simple. In the end, this is the kind of math that's wants to go more towards physics, because this is all what sound is doing, and you can't see sound and what it's doing. And this isn't exactly what the sound is doing, but it's analog to what the sound is doing. If you wanted a statistical representation of the refractioning of sound, you know, the combined tones in their pitch category, if you wanted just some kind of analog representation, this would be something. This would be close to that. In the end, you'd probably want, you know, some physics material. You know, they talk about each sound reverberates at a certain rate, and you can count the rises and falling in the reverberation and all of that, and you can do math with that. You can do calculations with that. You can see that the rate of this one is half what the rate of its position in the next octave is going to be, and on and on. There's a doubling effect, something called octavization, and there's some calculations you can do to assess what, okay, if you have 440 for A, to go the next octave up, what would you do? Well, 880 would fit. I mean, you can have variations of it, tune it to, you know, your will, but just for a comfortable standard that works, yeah, a doubling. So if you had this and you decide, well, I'm going to go one octave up, then you do simple math. Okay, well, let me calculate 440 for this A, multiply it by 2, and then go up to 880, and then you're at the next octave. So then go to your synthesizer or whatever, and you know, tune up the sound to 880, and there you have your next octave, and then go on and on. But yeah, it's all connected. Also, if you do chemistry, you're modeling chemicals or compounds, or if you're in the physics and modeling atoms, and then there's points where they connect and bond, and then there's numbers of points at which they bond, and then there's numbers of spots where there could be protons or electrons. There's you know, all kinds of stuff, architecture of the world. And even when you look at symmetry, lines of symmetry, axis, if you're looking at planets, you're looking at axis, and you're looking at the way things revolve around their axis, and Earth revolving around its axis, and even tilted, kind of like this is, and then another body, like maybe the moon, circles around that same axis, and the way the sun has its axis, and then all the bodies around it. So when you learn this and get used to it, you're not just learning music and developing skills for composing music. You're getting skills for a good mental framework to establish, you know, rationing with all kinds of subjects, you know. This is, they say music is a universal language, and then you talk to mathematicians, they'll say, well, mathematics is a universal language. And here, music, geometry, math, they meet, and you get a sense of what a universal language is. And if you can get music and math to meet, then you can get music and all the things that math meets, you can get them to meet music. Alright, we're going to come back with the next video. From here, the details can get a little bit more complex. So, just go over this, and I've already been doing it. I hope you're getting tired of it, because that means you've been hearing it as much as I want you to, which is the axis, the line of symmetry, things lining up. How do they line up? Where do you see them line up? Pay attention to them, look at them, see what else you can get that lines up, and then play them, hear them out, and hear the symmetry, the harmony that you're seeing. And if you hear it, plot it so that you can see it. If you plot it so that you can see it, play it so that you can hear it. And trust me, I've played some things and plotted them, and sure enough, if they didn't match in what I heard, they didn't match up there in the plot of you know, symmetry, and vice versa. Alright, on to the next diagram.